Have you ever wondered if we could travel back in time to witness history or jump forward to glimpse the future? It's a tantalizing thought that has sparked the imaginations of dreamers, scientists, and storytellers alike. Time travel, as a concept, has been a staple of science fiction, captivating audiences with its intriguing blend of possibility and paradox. From H.G. Wells' Time Machine to the TARDIS of Doctor Who, from the DeLorean of Back to the Future to the Time Turner of Harry Potter, the idea of bending time has always been a fascinating enigma. It's a concept that has permeated our culture, igniting curiosity and debate, shaping our understanding of the universe and our place in it. But is it just a figment of our collective imagination, or could there be a scientific truth lurking behind these fanciful tales? Today, we delve into the captivating world of time travel, demystifying the science behind it. Before we embark on our journey, we need to comprehend what time is. Time, my friends, is more than just the ticking of a clock or the turning of a calendar page. In the realm of physics, it's considered the fourth dimension. Imagine a three-dimensional world: length, width, and height. Now add time to it. It's the continuum in which events occur, from past to present to future. Time is an essential part of our universe's fabric, intertwined with space itself to form what we know as the space-time continuum. It's this continuum that gives us a sense of order, of cause and effect. It allows the universe to have a history, a present, and a future. But here's the kicker: time is not absolute. It can be stretched, squished, and warped by gravity and speed. This fascinating property might be the key to unlocking the mysteries of time travel. Now that we have a basic understanding of time, we can explore the possibility of manipulating it. Albert Einstein's theory of relativity holds the key to understanding time travel. Now, that's a sentence to kickstart our minds into gear, isn't it? Let's break it down. Einstein's theory of relativity is a game-changer in our understanding of the universe. It tells us that space and time are intertwined into a four-dimensional fabric known as space-time. But here's the kicker: this space-time fabric isn't rigid, it's more like a trampoline. When an object with mass, say a planet or a star, sits on this trampoline, it causes a dip, distorting the space-time around it. This distortion affects time itself. According to Einstein, the stronger the gravitational field, that is, the deeper the dip in our space-time trampoline, the slower time passes. This is a phenomenon known as time dilation. Let's bring this to life with an example: the famous twin paradox. Imagine you have a pair of twins. One stays on Earth while the other boards a spaceship and travels near the speed of light to a distant star and back. Now, because of the high speed and the gravitational pull of the star, time would pass more slowly for the traveling twin. When they return, they'd find their earthbound sibling has aged more. The twins, once synchronous in age, are now paradoxically different. This is time dilation in action. But what does this mean for time travel? Well, if we could somehow harness the power to travel at near light speeds or find a way to manipulate strong gravitational fields, we could, in theory, slow down time relative to others. We'd be taking a step closer to the realm of time travel. So while we might not be packing our bags for temporal adventures just yet, the seeds of possibility have been sown. Einstein's theory presents the first step towards time travel: time dilation. As we delve deeper, we'll uncover more tantalizing prospects that could one day turn science fiction into science fact. Imagine a shortcut through the fabric of space and time. That's a wormhole. Wormholes, these intriguing cosmic shortcuts, are a fascinating yet perplexing concept that has captured the imaginations of scientists and science fiction enthusiasts alike. In essence, they are tunnels connecting different parts of the universe, potentially even different points in time. The concept of wormholes comes from the field of theoretical physics, more specifically from Einstein's field equations of general relativity. These equations suggest that the fabric of the universe, space-time, can be folded and twisted, creating shortcuts between 2 points. In theory, a wormhole could allow us to leap across the universe or even across time itself in a fraction of the time it would take by traditional means. But before we start planning our time travel vacations, it's important to understand the challenges and uncertainties associated with wormholes. For starters, we've never actually observed one. Wormholes exist purely in the realm of mathematical equations and theoretical physics, not in the observable universe. Furthermore, even if we did discover a wormhole, there are some significant hurdles to overcome. According to current theories, wormholes would be incredibly unstable, potentially collapsing the moment anything tried to pass through. And let's not forget the enormous amounts of energy we'd need to keep one open. There's also the issue of size. Many scientists believe that if wormholes do exist, they might be microscopic, far too small for a human, let alone a spaceship, to pass through. And even if we could somehow enlarge a wormhole, it's unclear what would happen to anyone brave or foolish enough to enter. Would they be crushed by immense gravitational forces, or could they emerge unscathed on the other side? Despite these challenges, the concept of wormholes continues to captivate us, offering tantalizing, if elusive, possibilities for time travel. As we continue to probe the mysteries of the universe, who knows what we might discover? Wormholes, while theoretically possible, remain a tantalizing mystery in our quest for time travel. Time travel may sound exciting, but it comes with its fair share of paradoxes. Now let's dive into the labyrinth of time travel paradoxes, starting with the grandfather paradox. Imagine, if you will, a scenario where you've hopped into a time machine and traveled back to a time when your grandfather was a young man, long before your parents were born. According to the grandfather paradox, if you were to prevent your grandfather from meeting your grandmother, it would result in one of your parents never being born, and therefore you would never exist. But then, who traveled back in time? This conundrum is what we call the grandfather paradox, a classic example of the logical problems that arise when we contemplate the implications of time travel. Next on our paradox list is the bootstrap paradox, a concept that challenges our understanding of cause and effect. Picture this. You're a scientist who invents a time machine. One day, an older version of you appears, hands you a scientific formula, and tells you it's the secret to time travel. You study the formula and realize it's the exact concept you need to finish your time machine. Fast forward a few years and you, now older, travel back to give your younger self the formula. But here's the question: where did the formula originally come from? Both the grandfather paradox and the bootstrap paradox present significant challenges to the possibility of time travel. They force us to reconsider our understanding of cause and effect, and question whether we can change the past, or if the future is set in stone. The more we delve into the world of time travel, the more paradoxes we uncover. Each one presents a new challenge, a new riddle to solve. But rather than discouraging us, these paradoxes ignite our curiosity. They push us to think outside the box, to question the very fabric of reality. These paradoxes add to the complexity and intrigue of time travel. As we continue to explore the mysteries of time, the journey becomes all the more captivating. So buckle up, the adventure is only just beginning. So, where does this leave us regarding the possibility of time travel? The future of time travel is as exciting as it is mystifying. The field is ripe with research that pushes the boundaries of our understanding and challenges the very fabric of reality as we know it. One avenue of current exploration is the concept of wormholes. These hypothetical structures, a prediction of Einstein's theory of relativity, could potentially allow for rapid travel between two distant points in space and possibly time. However, creating a stable wormhole and traversing it safely remains a monumental challenge. At the same time, scientists are delving into the world of quantum mechanics. This realm of the very small might hold clues to the very large, including the nature of time itself. Some theories suggest that particles at the quantum level can exist in multiple places at once or even move backwards in time. Could this quantum weirdness be harnessed for large-scale time travel? The answer remains elusive. Then there's the cosmic scale. Some physicists suggest that our universe might be one of many in a multiverse, each with potentially different laws of physics. Could time travel be possible in another universe, even if it's not in ours? That's a question that might forever remain in the realm of the theoretical. Despite these tantalizing possibilities, the future of time travel is fraught with challenges. Practical issues aside, there are profound philosophical and ethical questions to consider. If time travel were possible, what would it mean for our understanding of free will, causality, and the nature of reality itself? While we may not be packing for a trip to the past or future anytime soon, the science of time travel continues to be a realm of endless possibilities and enduring fascination. The journey, it seems, is only just beginning.